Cranes play a huge role in modern construction and the manufacturing process. They contribute to the efficiency of logistics by facilitating the movement of heavy materials. There are types of cranes for specific processes, but in general, they all serve the same purpose: lifting. Cranes have been an integral part of human civilization for centuries, given that they can lift massive loads with precision and efficiency. But we will not leave them in the past. Cranes will become even more important in the future. They will progress along with our infrastructures and technology. The engineering behind cranes involves balance between strength, stability, and control. By calculating length, forces, and movements, we were able to create a crane of our own. A small prototype made just from MDF panels and screws. It can carry up to 650 grams. But we will not leave them in the past. Cranes will become even more important in the future. They will progress along with our infrastructures and technology. The engineering behind cranes.
The process of building this crane was a little bit difficult because we had to make two prototypes. The first one didn't succeed because the second arm, the one that was going to be pushing towards the wall, wasn't the right length. So we had to make our calculations again. After that, we were able to had the right length of the arm and build our prototype based on it. And in the building process, we were sure that once we were designing this crane, it wouldn't be too difficult because we did cut it in a laser cutter. But yeah, the only difficult thing we had to do was the calculations and also drilling the MDF because it was too fragile material. But the process was a little bit too good of building it, and it did succeed in the last prototype.
So the first thing that we did in the analysis was to obtain the centroids. This was important because we were going to use this data in the forces and the moments. So we started calculating the centroids in the original form, and we obtained that the centroid was in position 19.62 centimeters in X and 35.12 centimeters in Y. To obtain the forces, we had to do our free body diagram, which helped us do our symmetry of forces. And once we solved the symmetry of forces, we had some unknown values, which were solved with the moments we calculated later.
It's time to analyze our moments. We have four moments, one on each point. Since on point C, it's our origin, well, the moment will be 0, 0, 0. In point B, because of the arm that it's pushing towards the wall, because it's being pushed by carrying weight and also the weight of the crane, we have a moment there. Also, we have a moment in G, that it's the weight of the crane itself, and on A, that it's the weight carried by the crane. Thanks to that, we have the moments in Z, carrying a total of force exerted in B of 10,197 newtons.
After we obtained the forces and moments, we got the angles that were formed in the crane. We got that when the crane was in the original position, an angle of 60.62 degrees was formed, and when we inclined the crane 19 centimeters, the angle was of 78.63, which indicates that it got bigger.
As you can see, this is our final product, the crane that we did deliver. It was carrying around 1.6 kilograms, and yeah, in conclusion, we did had a perfect design for a stiff and durable crane, but the material wasn't the right one. As we noticed in the analysis, the second arm, the one that is pushing towards the wall isn't strong enough to hold a much bigger amount of weight. So we did have to consider a new type of material, more durable, if we want to put a little more weight on it. But yeah, the final product, it was a success. We did find some difficulties in the process, but at the end it all sorted out and it was all good to go.